Hi everyone. So in this video we are going to get an intuition of what value functions are. Value functions, as you know, are of two types. One is state value function and the other is action value function. So a state value function is represented by v pi of small s, and capital value action value function is represented by q pi of s comma a. What this means is, under the policy pi, what is the value of taking an action from state s, that is the state value function, or in other words, how valuable it is to start from state s, right? How valuable it is to start from state yes. And similarly, action value function represents how valuable it is to start from the state yes and take an action a under the policy pi. Pi here is the policy which is also represented by probability of taking an action a given that you're in a state yes. Policy is something, it is a rule under which the agent takes different actions, right? So the goal of a reinforcement learning problem would be to come up with a policy that will maximize the long term reward that the agent gets. So here we have a small grid world of 5 by 5 grid world here. 5 by 5. So this grid world has 25 states in total. The states are like this. States are represented by 0, 0, 0, 1. You can represent these states in any way. Actually, I chose this way to represent the states, and the actions there are of four types of actions are there in this. What are those? It is either to move up, down, left, or right. So one is up. So for moving up, the action up can be encoded as -1, 0, right? The row number should decrease and the column number should remain the same. And to move right, it is 0, 1, row number remains the same, column number increases. And then to move left, it is row number remains same, column number decreases, 0, -1. And to move down, it is 1, 0, row number increases, column number remains the same. So those are the four possible actions the agent can take at any point. So say the agent is in 2, 2, it can either take an action to move up, down, right, or left. You get the point, right? So now let's again see what these value functions actually mean. So the state value function is like a black box which takes state as the input, capital ST, the current state as the input, and tells how valuable it is to start from that state under the policy pi. Okay, so and similarly, state action value function tells how valuable it is to start from state yes and take an action a, right? It takes two inputs, s and action, and gives a number. This is simply how valuable it is to start from state s and take an action a, right? So we'll see how to calculate these values, how these action value and state value functions calculate the numerical values, right? Say consider a random policy. Okay, say pi is random, which means in our case there are four possible actions. So each action gets a probability of 0.25, right? The total probability has to add up to 1. So probability of taking each action up, down, left, or right will be equal to 0.25. So probability of taking, say, an action up given any state, let's represent it by capital ST, is equal to 0.25. Similarly, all the actions will have the probability of 0.25. Okay, so let's assume the agent is starting over here at 1 comma 1 comma 2 1 comma 2. So since our policy is random, at each time step the agent can take any action, right? It can either try to move up, down, left or right, and the episode will come to an end once it reaches the terminal state, the end state here, which is 4 comma 4. So depending on what action it takes, it keeps moving to different states, and it will the episode will come to an end when it reaches 4 comma 4. So we also had defined rewards in our first session, right? And the rewards were like this: when it reaches the terminal state, the agent gets a reward of plus 10, otherwise the reward will be minus 1 for every step it takes, right? Say for example it took a path like this, it might go right and then come down again right and like this, and say this is path 1. Path 1 got a total reward of say minus 5. I'm just writing any number there. So the total reward for path 1 was say minus 5, and say it took another path which was like this, which is a longer path. So path 2 might be minus 20, and say it took another path now which was like this. Say the path 3 got a total return of minus 2. So which is highest? Path 3 got the highest return, right? It is probably better than any other states. So even the path 2 had a similar distance, so it should also be minus 2, right? Or let's do one thing, we will increase the length of path 1, right? Minus 5. So path 1 and path 2 are longer than path 3, and hence the total return received by path 3 is the highest return, right? It is minus 2. So the agent can take different paths as the actions that it is taking are random, and when we take the average of all the different paths, what we get is known as the value of the state 1 comma 2, right? Let me write that down. So if you take the average of all this, minus 5, minus 20 and minus 2, it is known as v pi of, what is it, 1 comma 2. How valuable it is to start from 1 comma 2 is given by average of the total returns of each episode, right? That is how valuable it is to start from that particular state under the random policy that we have. We can come up with another policy, a different policy. Say the policy can be to move always right or to move say always down, and it will give a different path in each episode, right? Sometimes it might not reach the terminal state at all. So like this, every reinforcement model can come up with a different policy, and our goal is to come up with a policy which will maximize the value of every state. Here we have 25 states, so all the 25 states should have maximum possible value. Let's get we'll get to that in a moment, but we'll try to find out what the actual value of this state 1 comma 2 is by simulating the same problem many times. So now let's go back to the code that we discussed in our first session. Here it is. So what do we have here? The starting state, let's change the starting state to the one that we are discussing here. What is it? 1 comma 2, right? 1 comma 2. Let me change the starting state to 1 comma 2, and the terminal state is 4 comma 4, and the rewards are 10 for reaching the terminal state and minus 1 for every other step it takes. So let me scroll down. Yeah, here what we have is, uh, in this while loop, we keep running the while loop until the agent reaches the terminal state, right? Until it reaches 4 comma 4. This is one episode. So like this, we simulate many episodes using a for loop. How many episodes are we simulating? 10,000 episodes, and we'll average the total return over 10,000 episodes to check how valuable it is, that particular is that particular state, right? Let me run the cells now. So 1 comma 2 is the state that we are looking at. I'm running the cells one by one, so it will take around a couple of minutes to run. So once again, what is happening here, we simulate the agent by taking random actions over multiple episodes, and take the average of returns from each episode, right? Total returns from each episode. So let it run, and we'll see how what would be the expected reward. It's taking a long time because our policy is random, so it might wander around like an ant before it reaches the terminal state, and this has to happen 10,000 times, right? So it will take some time. Okay, so the average total reward for starting from that state is minus 85.64, right? Let me write that number here. What was it again? Minus 85.64. okay, minus 85.64 for starting from 1 comma 2. So now let's try it for another state. Let's try it for a state that is closer to the terminal state. Let's try for 3 comma 4 and see what would be the total reward. Once again, why are we taking average? Because from this point the agent can take any path like this, right? It can go anywhere because the actions are random, and hence we want to take the average return that the agent takes from 3 comma 4. So the average return is nothing but how valuable it is to start from the state 3 comma 4, right? Let me go back to the code and change the starting state to 3 comma 4. Three comma 4, and then rerun it. It should converge faster now. As we are close to the terminal state, one of the 4 actions will take it to the terminal state in just one step. So as you can see, it is running faster now. We are minus 37.0018. So this is how valuable it is to start from 3 comma 4 by taking random actions, right? It is the average total reward return that we get for starting from state 3 comma 4 when we are taking random actions, right? I'll write this number as well over there. It is around sorry about that. Let me find the pen. Minus 37.00. Do you see that it is of higher value to start from 3 comma 4 compared to starting from 1 comma 2, because just in one step the agent will reach the terminal state by starting from 3 comma 4 compared to starting from 1 comma 2. From 1 comma 2 it can wander anywhere, and the chances of reaching the terminal state sooner is very less, right? So I have filled up all the values here. The values are like this for starting from each of the states and reaching the terminal end state. Okay, So for starting from the end state, we don't get any reward because we assigned rewards only for reaching to the end state, not for starting from end state. From end state we can't go anywhere. The agent the episode will end there, right? So if you see here, the lowest value is of the state 0 comma 0, which makes sense, and the highest values are here, which is one step. All the other values are like a slope to there. So now for we got all these values for one policy, random policy. Let's call that pi 1. Okay, so there can still be another policy pi 2, right, for which like we might get better values of each state. What I mean by that, v pi 1 of state might be less than or equal to v pi 2 of state, right? Again, there might be a policy pi 3 which might be better than both the policies pi 1 and pi 2. So this can keep going on until we reach a pi which will maximize the value function, and that is known as the optimal policy, right? Pi, it is represented by pi star. It is known as optimal policy. So now let's try to simulate the same thing using a different policy and see if the values of each state change. Okay, let's go back there. In the first session, if you remember, we had one of you had answered a better, what could be a better policy for this, which was to take actions like this. It is either to move down or to move right at any given point. So we avoid the actions moving up and to move to the left. It makes sense, right? We are starting from somewhere on the top or left side, and we want to move to the bottom right corner of the grid. So if we took those actions, let's see what would be the average total return. Now we have a different policy. Let's call this pi 2. Pi 1 was random among the 4 actions, so pi 2 is either to move down or to move right, another decision. So now as we can see here, what state was this? For starting from 3 comma 4, how valuable is to start from 3 comma 4 is 8.9947, right? Let me compare it with the old value that we had. So 3 comma 4 had minus 36. Now it is 8 point something, right? So the value of this particular state has certainly increased by taking this action, which is intuitively better. So let's try it for some simulate it for some other state. Let's try it for 0 comma 0 itself. Under our second policy, which is intuitively better, let's try doing it for 0 comma 0. Okay, it's running. Do you see that? Isn't it better than the previous value that we had for 0 comma 0? Now the value for starting from state 0 comma 0 under this policy is 0.78, right? See, now it is 0.78, which is much higher than the value that we had earlier. So like this you can calculate it for every state, and it will be much higher than the instead of taking random actions. So that is how we can tell this expression, right? Value of starting from state, any state under the policy pi 1 is less than value of any state starting from pi 2. And there exists one policy, one decision making. Under that policy, every state will have the highest values, and that is known as the optimal policy. The goal of reinforcement learning is to come up with an optimal policy, right? Okay. Now we have a function that needs to be maximized, and thus there are many ways to maximize the value function. We'll see that in the coming sessions, how to maximize these value functions.